All right, welcome back everybody. So we are going to be finishing chapter 8 today. Unfortunately, it's remote again, so for me it works better doing pre-recorded. So let's go ahead and switch over. So I think this is where we stopped on chapter 8, which is slide 28. We were in the middle of doing hypothesis testing, setting up everything that we're going to need. So these are some basic assumptions that go into hypothesis testing. Some of these are familiar, so random sampling. Again, when we talk about assumptions, it's the idea that you're doing everything correctly. Sometimes there are tests for making sure that it is in fact a normal distribution, for example, or that other things are fulfilled. In this case, random sampling is going to be the first one that we want to make sure that is that assumption is fulfilled. The second one being independent observations. So this means that if your observations are participants, that the two participants do not interact with each other. So the fact that you ran participant 1 isn't going to influence the data that you get from participant 2. So independent observations, independent data, so to speak. This does not have anything to do with between subjects design. This just has to do with making sure that the fact that you ran a person isn't going to influence another person that you're going to run, right? Staying in the naive state. This third one is that your standard deviation is going to be unchanged by your treatment. So this is what I've been showing you. I know that gets a bit abstract sometimes, but the idea is that we have a known population that we're pulling from with a mean and a standard deviation, and the idea is that if we do the treatment on them, it's going to change the mean, right? They might increase their scores or decrease their scores, but the standard deviation shouldn't change. So you can see here, it's still showing sigma as the same value. And the idea is that whatever treatment that you're doing, think of it as adding or subtracting a constant, right? Such that all individuals are shifting up in their scores or down in their scores equally. Such that if you took that distribution and got the standard deviation, it would be the same as it was before. Also, a note here, the random sampling, as long as you're doing your random sampling correctly, usually your second one will follow suit, right? If it is entirely random and you're not just picking from like 10 friends who know each other, then your observations will be independent. This fourth one we've talked about on and off is that you have a normal distribution, so a normal sampling distribution. Okay. So we had talked about a few things regarding the hypothesis test. That was the last one, was the assumptions. So we're going to move into one-tailed or directional hypothesis test. And this is when, so far when we talk about hypothesis testing, you're saying your alternative hypothesis, right? Your null hypothesis says nothing is going to change. The alternative hypothesis says something will change, but you don't necessarily know in what direction. Will it increase or decrease? You're just saying, and you're testing for there being a change beyond what would be expected in the untreated population. A directional hypothesis says, I only think it will go in one direction. It will only increase or it will only decrease. So this is why we call the other one two-tailed hypotheses often. And when we talked about it, right, we looked at the critical region in the tails. As long as you're falling in the critical region here, you can reject the null hypothesis. For directional hypothesis, you're only looking at one of those tails. So for example, let's just say a phenomenon, eating food makes you more full, right? We could probably confidently say that only goes in one direction. We're not going to think that if people are eating food, that it goes in the opposite direction, right? That they become more and more hungry. Eventually your stomach fills up. Toddlers learn more words as they get older. And it can also be on the other end, dementia causes one to have worse memory. If you have the diagnosis of dementia, it's unlikely that you're actually going to increase your memory capability than what you had before. But I'll get to a word of caution because I am mentioning this because it's important to know that there is one- and two-tailed tests, but for the sake of argument, you're always going to use two-tailed tests, right? So this directional or one-tail hypothesis, not very common to actually use this. Even if you think that it goes in one direction, you want to play it safe and propose a two-tailed hypothesis. So going back to the example of if a waiter is wearing a red shirt or a female waiter server is wearing a red shirt, that men are going to increase their tipping behaviors. So if you were to pose that as a wait, did I state this correctly? These are like reversed. With the red shirt. Okay, I always put the null hypothesis first. I don't know why I didn't do that here. Here, the alternative hypothesis is that, which is your actual hypothesis, with red shirts, the average tip is going to increase, be greater than 16%. When you put the null hypothesis, remember, the competing hypotheses, they are mutually exclusive and comprehensive. So if your alternative hypothesis is that it's going to be greater than 16, the other hypothesis is equal or less than 16. You do have to put that equal in there. Plotting it, we're only talking about one tail. We want to see if the group that we get is significantly different from the distribution if the null hypothesis was true. So here now, this is where it's different from a two-directional hypothesis, two-directional test. So locating your critical region, we're going to use an alpha level of, say, 0.05, right? Pretty standard. But here the difference is that that 5% is not in both tails, it's entirely in one tail. So that's going to change your z-score. You know, this 1.96 that hopefully you guys are getting familiar with seeing. For a one-tailed test, because all 5% have to be in that tail, it ends up shifting it down, and you only need to reach 1.65 for a z-score, meaning you have to be above 1.65, right? And so this is a bit risky because people can, this is why I mentioned this, it's easy to do smudging, right? You run your data, it's not significant at 0.05 with a two-tailed hypothesis. So then you go and you run the test again, but with one-tailed, right? And you're like, oh, well, you know, as long as I can get the statistic to be significant, and often it will actually end up being significant. So, like I said, much, much safer to have your hypothesis two-tailed. You also might be wrong, right? You might think something is going to increase when in fact, empirically, nature is going to actually have it decrease. Sometimes we don't know what we're studying. So especially when it's exploratory, but just in general, always use the two-tailed hypothesis. Okay. So effect size. This and power are the last two important parts of hypothesis testing. So when we say that something is statistically significant, that is not the same as saying that the treatment effect was very, very large, right? You're just saying that the two populations, the treated and untreated, are different, seemingly are belonging to a different group because it would have to be such an extreme sample, right? Based on your alpha level, we're going to say, well, at like 1%, that is probably entirely different distribution. That's not the same as saying that my effect is really strong. And we talked about this in class. When we study psychological phenomenon, these effects are often very small. For one, because it's so hard to put your finger on it and to objectify it and measure it properly. So a hypothesis test doesn't reveal any information about how strong or large your effect was, only that it was significantly different than the null hypothesis, meaning that no change happened. So it does establish that results are very unlikely to occur if there is no treatment. That's what I just said. So the way that a hypothesis test does this is, of course, calculating the standard error. We've been talking about that. That was chapter 7, was all about the standard error, not standard deviation, but now the standard error. So it's a measure of how much is reasonable to expect from the sample that you pull from the population. How much is reasonable to expect that sample statistic to be different than the population's parameter. I almost said statistic. Population parameter. For example, mean. Mean is the main one that we've been talking about. And you're showing that it's statistically significant by demonstrating that that mean difference is larger than the standard error. So if we do want information about the treatment effect, this is what we can do a calculation that gives us the effect size. So treatment effect, the treatment effect size of whatever it was you were doing. It's called Cohen's d, and it's a ratio of the mean difference, right, treated versus not treated, over the standard deviation of the population. Because we don't actually have the value for the treated population, right, we have the treated sample, and we're saying that hopefully my sample is representative of the population. So more appropriately, we call it the estimated Cohen's d, and we replace not mu of the population, but the mean of your sample that was treated against the mean of the population without treatment, which is your null hypothesis, right, over the standard deviation. So what this is showing here, between two different distributions, one with a standard deviation of 100 versus a standard deviation of 15, having a 15-point difference will look very different between these two distributions, right? Because a 15-point difference down here is already going to be the actual standard deviation, whereas up here it's going to be a lot smaller. So you can see D here, this is the Cohen's d. Our effect here of our treatment is 0.15, whereas our treatment effect here, because the shift that occurred with your treated sample is as large as the standard deviation, it ends up being 1.0. So when it comes to evaluating whether your effect was strong or not, right, not statistically significant, but if it was a strong effect, excuse me, these are usually the ranges, the ballpark of what we ascribe to each of the Cohen d values. So if it's around 0.2, that's considered a small effect. So right over here we have 0.15. That's going to be a small effect. A Cohen's d of 0.5 is a medium effect, pretty solid. And a Cohen's d of 0.8 is going to be a rather large effect. Of course, if we're above 1, then that's also going to be a very large effect. Anything beyond 1 is going to be very large. An important thing to note is that Cohen's d is irrespective of the size of your sample. This is taken from the slide that we covered in class when we talked about the standard error being sensitive to how large your sample is. If you have a sample of only 25, your z might only be 0.5, which is not going to reach the alpha level that you're looking for. Whereas if you run 400 400 people, your z-score is actually going to be in that critical region because it's past the magical number 1.96. But for Cohen's d, it doesn't matter what the n is because all it's looking at is the mean difference, right, from 50 to 51 over the standard deviation, which is going to be 0.1. So this was actually a rather small effect. Also, I mean, you know, 50 to 51 for 1, that's like 1 point. And with a rather large standard deviation of 10, we can already kind of do this in our head where we're like, this wasn't a very large shift, right? If I ran 400 people, it would be significant, but it's a small effect. Coming back here when we did the hypothesis testing on whether or not waiters who wear a red shirt are tipped more, you know, we calculated the z-score and it was significant and everything was great because it went from 16 to 17. For Cohen's d, all we need are those two mean values and the standard deviation. So with that difference divided by 3, 0.4, which is 0.4, if you remember, we have 0.2, 0.5, and 0.8. So 0.4 is, I would say, a solid medium effect. You know, not only significant in this case if you're running 36 people, but it's also a medium effect size. Okay. All right, the last thing, that was effect size. The last thing is statistical power. So when you are setting up your hypothesis, there are a few things that you're planning before you actually start, right? In the case of the class where I'm making you do a research study, I told you run 5 people. We're realistically going to be working with 0.05 alpha level, and you're going to be doing a two-tail test. But when you're running a study and you get to design it yourself, you get to choose your alpha level. You know, maybe you want it at 0.01. Maybe you want to mitigate the risk of that type 1 error. Make sure that when it's significant, that means an effect actually happened, right? Type 1 error means you rejected the null hypothesis, but there was not actually anything there happening. The other big question is, how many people are you going to run? Because as we saw, the amount of people you run affects the standard error, right? And the standard error is going to affect the z-score. But running how many people you're going to use also affects the power. So will we have the power to detect a treatment effect with this sample size? With a sample size of 5, you probably have a very low amount of power to actually detect that, that treatment effect. So taken from the book, whenever I have these quotations, I take this directly out of the book. The power of a statistical test is the probability that the test will correctly reject a false null hypothesis, right? False, it's just you're going to successfully reject the null hypothesis. This is the probability you have of actually going through with that. So the power is the probability that the test will identify a treatment effect if one really exists. So if a treatment had an effect, right, there's 2 different outcomes. You actually failed to reject the null hypothesis, even though the effect was there. That's a type 2 error. That's not so bad. You just didn't have, you know, enough people or enough power, right, which is related to how many people you have. You didn't have enough power in your study to successfully reject the null hypothesis and go with your alternative hypothesis. So you're just like, oh, got to run the study again, but better, probably with more people. The other one is that if you reject the null hypothesis when there was a real effect, which is what we want. So this type 2 error, we gave a symbol of beta, even though it's really difficult to assess beta, because there's a lot of factors that go into it. It's not just how many people you have. So when we actually successfully go through and reject a null hypothesis, we can assign it 1 minus beta. And again, this is going to be probability, so that's what the P here is. Probability of rejecting a false null hypothesis is 1 minus the type 2 error. So how would we calculate this? So let's take a sample of, or rather a population with a mean of 80 and a standard deviation of 10. So if we take a sample of 4, only 4 people, what is the power of the hypothesis test if we expect a treatment increase of 8 points? So we're going to go from 80 to 88 and see, for 1, is this significant? But what is the power? What is the probability that I'm going to successfully reject the null hypothesis? So with these numbers, first thing we can do is calculate our standard error. This should hopefully be really familiar by now. Standard error, right, when it's sigma with an M here, this is standard error of the mean, or of the sample mean. Standard deviation over the square root of how many people you're running. So 4, and then 10 we grab over here. It gives you a standard error of 5. So we can plot this, and this is going to end up with you're going to end up with 2 different distributions. This distribution reflects the null hypothesis distribution, so no effect happened. We stay at 80 with a standard error of 5, and this is what my guy looks like. The other one is your alternative hypothesis distribution, right? If you're hypothesizing that there will be an 8-point increase, that means you are shifting your distribution with the same standard error and the same standard deviation, right? So we're keeping here the standard error the same, but now we're trying to actually figure out what is your power. So what proportion is this shaded region, right? The one that basically was shifted, and that alternate distribution is in the realm of the critical region, right? Again, the critical region is where we reject the null hypothesis, and it would be over here with the tail. Again, magical number 1.96. This should tell you you're looking at an alpha level of 0.05, right? So from 1.96, this is how much this whole shaded region is the critical region within the alternative hypothesis distribution, right? So this 1.96, the sample mean that corresponds to this z-score, but in the alternative distribution, is called the critical sample mean, and we're trying to calculate what is that critical sample mean. So basically, if my alternative hypothesis, if I'm going to end up supporting my alternative hypothesis and I end up shifting 8 points over, at what sample mean do I have to be above that in order to be within that critical window, critical region of the null hypothesis? So this shaded window, or this shaded portion, that is your power. So it's a certain amount of proportion or distribution, part of the distribution, right? Percentage of the distribution. So how likely are we to have our alternative hypothesis in this critical region? So hopefully you should have some alarm bells going off to figure out how you would actually do this. And when we talk about the area under the curve, right, the proportion of your distribution, hopefully you should be thinking unit normal table, right? As long as I have a z-score, I can figure out what the proportion is, and then afterwards you can go and calculate the critical sample mean. Or rather, you're going to first figure out your z-score, then calculate the m-critical, and then figure out your proportion. All right, so step 1, you have a z-score of 1.96. We can rewrite this. This is the same formula that we keep rewriting when you're trying to assess a score or a sample mean, but now we're just plugging in specifically for the critical sample mean. Sorry, I thought someone came through the door. The null hypothesis mean, right, that nothing changed, which would be 80, and then the z-score for that particular alpha level, and your standard error, which is 5. So we just plug those guys in, 80, our fabulous z-score, our standard error, and then we get 89.8, which, as you can see, almost 90. That looks pretty good. That would be the corresponding sample mean, because again, this is a distribution of sample means. So in order to calculate the power, sketch out these two distributions. Now we're not just doing one distribution anymore. It's because you have your null hypothesis distribution, and then you shift according to your alternative hypothesis in the direction that you think that's happening, with the expected amount of effect points, right? An 8-point difference. So it's going to be the distribution for your alternative distribution, or your alternative hypothesis. All right, step 2 is locate the critical region and compute the sample mean for that critical, the critical sample mean, rather. So you have your z-score, or rather you have the z-score for the null hypothesis distribution, which is 1.96. I don't know why my brain's farting right now. Yes, you're trying to find what the corresponding sample mean would be for that critical window. I keep saying window, the critical region. And then you can actually compute the z-score for your alternative hypothesis and find the power, right? Because that critical region and the z-score is what you have to be above. But for you saying I have an 8-point increase, you actually need to calculate the z-score for this area here. So to calculate the z-score, we need two things. We need our expected value, right? This was our hypothesized. It's going to be an 8-point increase. And we had just calculated the critical sample mean, which is 89.8. So we're trying to see this, you know, filling in this gap here. So our Z calculation, you know, a mean difference between our sample and our alternative hypothesis over the standard error gives us 0.036. So what we do here now is look this up in the unit normal table. What proportion corresponds to this Z-score? So think about it really quick, which column you would look this up in. We have 0.36, and you can see we're looking at a tail because it's not over the 50% proportion, right? So we're going to look in column C, which is for the tail. So the way we would formally write that, what is the probability of Z being above 0.36, which is the region that we would, you know, this proportion here? 35%. So if we select a sample of only 4 people and expect an 8-point increase, we only have a 36% chance of actually rejecting the null hypothesis. So it's not actually a lot, and it's also only 4 people. So let's talk about that, because sample size is very much, or rather power is very much tied to your sample size. So same numbers as before, we're expecting an 8-point difference. We start at 80, we're going to be shifting to 88, but now we increase our sample size to 25, not 4. Our standard error changes because it's influenced by our sample size. So now our standard error is 2. So we've collapsed from a standard error of 5 to 2, makes it a tighter distribution. And you can already see here the shift from null hypothesis distribution to alternative hypothesis distribution is cleaner separation. But more importantly, once we identify that critical region, you can see much more of the alternative hypothesis distribution falls in that critical window of the null hypothesis distribution. So step 1, sketch it out. Step 2, calculate what that sample mean would be, the critical sample mean. Plug in our numbers. Everything stays the same except for our standard error changed. So now we're at 83.9. So you notice this is lower, right? Because with a tighter distribution, we actually, that critical area is a smaller step before we actually are inside of that critical region. Step 3, calculate the Z-score, right? Not the Z-score of this guy, the null distribution. Calculate the Z-score of this guy, the alternative hypothesis. So we get negative 2.04, and hopefully negative 2. You're realizing, aha, this is, you know, for one, this is past the standard deviation, right? It's past 1.96. But if you look this up in the table, again, look at your sketch, figure out which column you're going to use. You're not going to be using the tail for this one. The majority of the distribution here is under your curve that's colored in, so you're going to be using the body, so column B. And that corresponds to almost 98% power. That's pretty big. So you're like, I got a lot of power with only increasing from 4 to 25 people. That was the only thing that changed in this, is your N. Okay. The power is also related to the effect size. We talked about Cohen's d. There is a relationship there as well. So now we're not going to talk about, we're going back to the original 4 people that we're running, but we're not going to do an 8-point increase. We're going to suggest a much greater effect size. We're looking for a treatment effect of 16. So sketch out step 1, sketch out your 2 distributions, right? You're going to have a new expected value, not 88 anymore, but 80, here, 80 plus 16 puts us at 96. Did we already have the critical? Oh, yeah, that's right. So here we don't need to calculate the sample mean critical anymore because the number here is the same as before. So n equals 4. So we actually have the same one, the same critical sample mean as before. The only thing that's changing here is the size difference between those 2 means. And now our z-score is negative 1.24. Again, look up the proportion that it corresponds to, which column. It's going to be column B, the body. It is B, right? Sometimes yeah, it says it right there. The proportion, the probability of Z being beyond 1.24 right here, the negative and plus sign don't matter when you're looking up the Z-scores, but you want to sketch it so that you know where you're talking about. But that corresponds to 90%, right? Before, what we had with 4 people and an 8-point shift was, I think, 35 or 36% power. Now, increasing our treatment size has increased our power, where we're up to 90%. So hypothesizing a greater effect size gives you more power. Cohen's D for this guy, 1.6. That's above 1. That's a very large effect size, right? We're proposing a large effect size. So you can kind of see how these guys are related. Effect size doesn't use N, but otherwise N influences your power, influences your standard error. Your N matters. So when you're setting up, you're doing your hypothesis preparations, how many people you're going to run is important. So 5 is not going to be enough, but in the case of what you guys are doing, this is practice, right? This is practice and understanding how would you run a research study. Yeah, so as effect size increases, the probability of rejecting the null hypothesis increases, which means your power increases. Now, as far as whether or not this will be statistically significant is a bit of a different question, right? You're proposing a really big effect size, or rather treatment effect. You also want a large enough N so that hopefully it will be statistically significant. So there is a trade-off, right? Power tables, I think this is it in the appendix? Actually, I don't remember if this is in the appendix or not. No, this one wasn't in the appendix. This was in the chapter itself. So we have these power tables, and you can see here on the top whether or not you're looking for a medium effect size or a small effect size, 2 tails. Oh yeah, it's 2 tails for all of them, but what changes is the alpha level. So both of these are 0.05, these are 0.01. And you can see basically your whichever effect size you're going with, or what your critical region is going to be, meaning your alpha level, influences how much power you have. So what these are showing, all of these numbers, is the size of the sample you need to reach that particular power level over here. So for example, if I want a medium effect size, and let's just say I want to have a lot of power, and say 90% power, right? And I'm going to use an alpha level of 0.05. I come all the way down to here for 90% power, you know, likelihood of actually successfully rejecting the null hypothesis. I need 43 people. And people actually do this before they plan a study. They'll look up power tables and do power calculations and figure out how many people they need to run to actually get there. Because we put time and effort and money into these things. We don't just want to waste an experiment. So often we'll do this beforehand, figuring out how many people. But now, if you, for example, switch over here, same effect size, sorry, same effect size, but with a more stringent alpha level of 0.01, you need to run more people before it can be statistically significant. And if we look at effect size, right, if I'm going with if what I'm hypothesizing or what I'm dealing with, like some kind of cognitive function, ends up being a smaller effect size, you have to significantly run more people, right? So these 3 things are connected. Even if effect size and sample size are not influencing each other, when it comes to power, those 3 are connected to one another. Okay. And yes, also I had mentioned this in that last table, your alpha level. So you would, we don't want to commit a type 1 error. If you commit a type 1 error, that means your study said, I'm significant, look how cool this is, when really nothing actually happened, right? So the way to get around that is to lower your alpha level so that you don't run the risk of the type 1 error. But when you do that, there are consequences to it. So here, This looks like the same graph as before, okay? So now if you want to lower your alpha level, right, 1.96, this was an alpha level of 0.05, but let's say you want to move this to 2.5, which would be, or 2.6, which would be an alpha level of 0.01. You can see what you're like putting my hand on the screen as if you can see it. Shifting this boundary to over here. Actually, didn't I have a line there? Yeah, you're shifting this boundary over here, and now you have lessened your power because you lessened the proportion that is under the curve. By lowering your alpha level, you lower your power. I thought I had more on the side, but yes. So there's a direct relationship between those. So not always best to lower your alpha level. That is why alpha 0.05 is kind of the gold standard. Okay, last thing, back to our directional hypothesis. Let's say you your hypothesis is that it only increases or only decreases. In this case, let's say something decreases, right? Like the reading at night decreases your attentional capabilities the next day if it's a e-reader with a screen. So here when you do step 1 and you sketch out your distribution, just make sure that you're putting the alternative distribution on the correct side. So you would hypothesize it's going to decrease, but then everything else is the same. You have 1.96, you're trying to figure out what M does that correspond to, what's my critical M. Just make sure that you're subtracting, right? So far we said the mean plus Z times standard error. Now you have to do minus, but then otherwise everything else is fine. Once you do your Z calculation, you don't need to be concerned about negative or plus, right? Then you look it up in the table, you get a percentage or a proportion, and then otherwise it's the same. So this is why that step 1 is pretty important, to make sure that if you have, especially if you have a directional hypothesis, you are mapping it out correctly. And that was my last slide. Look at that. So it might end up being a really quick run through. I think usually when I do this in person, I'm a little bit slower, but the advantage when it's recorded is that you can actually go back and view it, right? So next week we are tackling chapter 10, oh wait, 9 first, sorry, chapter 9 and 10. So all of this builds on itself. We're going to be adding, well, I'll let the hypothesis test sink in for now, and then we'll tackle next week. All right, guys. Email me if you have any questions, and we'll keep on chugging along next week. All right, bye.